Back at it, guys. We are looking at our island chains and we're getting ready to expand. Now let me kind of remind you some things that we've already done. Okay, we have kind of two island chains that guide us in how to do the problems here when we're relating numbers of atoms to mass of an element and number of molecules to mass of a compound. So if I've got numbers of atoms, I can use Avogadro's number to go to moles of that element. Once I'm in moles of the element, I can use molar mass of that element to go to mass of an element. Okay? Same thing if I have number of molecules or formula units. Remember, molecules for covalent compounds, formula units for ionic. I can use Avogadro's number to give me moles of compound. And then I can use molar mass of the compound to give me mass of the compound. So these are two parallel tracks, depending on if I'm dealing with an individual element or an individual compound. What we're going to do now is look at going in between these two island chains. Okay? There's a connector right here, and it's called the mole ratio. Okay? The mole ratio is exactly what the name implies. It's a mole relationship between a compound and the elements in the compound. So for right now, our mole ratio is a mole to mole, okay, relationship between a mole of a compound and the moles of individual individual elements in the compound. Now, when we start doing reaction stoichiometry, we'll expand out our definition of a mole ratio, but for right now, that's our relationship in a mole ratio. So let me show you, okay, an example here. So if I have a formula of CH4, I could ask you a question like, how many grams of hydrogen are there in a 21.3 gram sample of CH4, common name methane? Well, we know that 1 mole of methane has a mass of 16.0426 grams. I got that by adding together the mass of 1 mole of carbon and 4 moles of hydrogen. And our mole ratio is for every 1 mole of CH4, there are 4 moles of hydrogen. Because see that little subscript 4 there? There's 1 carbon to 4 hydrogens. So 1 mole of this contains 1 mole of carbon and 4 moles of hydrogen. And 1 mole of hydrogen has a mass of 1.0079. Okay? So kind of looking at our island chain and guiding ourselves through, we're starting out with grams of a compound. So we're going to use molar mass of the compound to go to moles of the compound. Then we're going to use our mole ratio to get to moles of an element. And then we're going to use molar mass of the element to go to grams of an element. So let me run through this for you. Okay, I'm going to have to erase our pretty islands. But, you know, if you need to, go back and freeze frame on those and write that down. Okay? So we were starting out with 21.3 grams of methane. Okay? It's going to take us 3 steps. Following our bouncing ball, the first thing we're doing is going from grams of methane to moles of methane. So there's 1 mole of methane for every 16.046 grams of methane. So notice grams and grams of methane divide out. Now I'm going to use my mole ratio. There are 4 moles of hydrogen for every 1 mole of methane. So now moles and moles of methane divide out. And then there's 1.0079 grams of hydrogen for every 1 mole of hydrogen. So moles of hydrogen divide out. So if we pop this through, 21.3 divided by 16.04 times 4 times 1.0079, 3 significant figures, I get 5.34 grams of hydrogen. Okay? Now, guys, I can't stress enough how important it is that you guys write out a pathway. I'm going to start out with grams. I've got to go to moles. That means I need molar mass. The organization of these problems, that's the tricky part. Once you get it organized and you know the steps you're going to have to do, it's just a matter of stringing those conversion factors and making it work. So I want you guys to practice that. So let's look at problem 14.3 on page 185. Okay, so page 185. Okay, we're going to look at 14.13 here. Okay. Now we may try both of these just because you need as much practice as possible doing these kind of problems. So let's look at for practice and then we'll look at more practice, okay, on these 2 problems. So the first one says determine the mass of oxygen in a 7.2 gram sample of aluminum sulfate. So we know that we're starting out with 7.2 grams of aluminum sulfate. Okay, and we're asked grams of oxygen. Now, let's kind of step ourselves through this. Okay, we're going to have to go from grams of aluminum sulfate to moles of aluminum sulfate. And then we're going to go to moles of oxygen and then to grams of oxygen. So it's going to take 3 conversion factors. If you can write this down, you understand what you're doing. It's critical, guys. So right here, I need to get the molar mass of aluminum sulfate. So 1 mole of Al2SO4 taken 3 times. So let's start adding things up. So I've got 2 aluminums. So 2 times the molar mass of aluminum. And guys, I'm using the periodic table at the front of your book. So 2 times 26.98 plus, I've got 3 sulfurs, 3 times 32.06 plus 12 times the molar mass of oxygen, so 12 times 15.9994. So I get 1 mole of aluminum sulfate has a mass of 342.1328 grams. Now before you freak out, we've got 12 oxygens and a sulfur. The mass piles up pretty quickly. I'm running the numbers again just to double check. Yep. So we've got that. Now, looking at the formula, for every 1 aluminum sulfate, there are 4 times 3, 12 oxygens. So 1 mole of aluminum sulfate contains 12 moles of oxygen. And then 1 mole of oxygen has a mass of 15.9994 grams. So I have all my tools. See how I've got everything nice and neatly organized here? So I've laid out what I want to do, and then I went and collected all of the relationships. So 7.2 grams of Al2SO4 taken 3 times. Our first step, 1 mole of Al2SO4 in parentheses with a 3 for every 342.1328 grams. Al2SO4 taken 3. So notice grams and grams of aluminum sulfate have divided out. Next, we're going to go to moles of oxygen. 12 moles of oxygen for every 1 mole of aluminum sulfate. So now, moles of aluminum sulfate divide out. And then lastly, 15.9994 grams of oxygen for every 1 mole of oxygen. So moles of oxygen divide out. The only unit I'm left in is our grams of oxygen. So now I can touch my calculator. See how much work we had to do before we got to our calculator? So 7.2 divided by 342.1328 times 12 times 15.9994 gives us an answer of 4.04 grams of oxygen. Okay? Now, the devil is in the details here. It's how you set it up. That's going to be all the difference. Now, let me look at that other problem there and see if that's one that I feel we just have to do or if we can move on. Yeah, the other one's got some other stuff in it, but it's not anything that I feel is super critical for us to do. So let's move on. Okay? Our next kind of problem that we're going to face is a mass percent composition. Now, lots of times when we experimentally look at a compound, we're going to be worried about breaking it down into its percentage of each element. Okay? So first thing we're going to do is we're going to go from a formula to percent composition, and then we're going to look at going from percent composition back to formula. Okay? Now, percent composition is going to be percentage of each element. Okay, so let's talk about percent composition. We're going to calculate mass percent composition by looking at the molecular formula for a compound, the empirical formula for an ionic compound, and then we're going to take an experimentally determined one and go backwards. So we're going to get percent of an element is the mass of that element in 1 mole of compound divided by the mass of 1 mole of the compound times 100%. So I'm going to start out with some simple examples and work up to something a bit more complicated. Okay, so let's say we had methane, CH4. Now, 1 mole of methane contains 1 mole of carbon and 4 moles of hydrogen. So 1 mole of carbon is 12.011 grams of carbon. 4 moles of hydrogen is 4 times 1.0079 grams of hydrogen. Okay? So 4 times 1.0079, that's 4.0316 grams of hydrogen, of 12.011 grams of carbon. If I add those together, I get 16.0426 grams as the molar mass of CH4. So our percent carbon by mass would be 12.011 grams divided by 16.0426 grams times 100%. So 12.011 divided by the 16.0426 would give me, times 100, would give me 74.87% carbon. Okay? Our percent hydrogen would be 4.0316 grams of hydrogen, or grams, divided by 16.0426 grams times 100%. So 4.0316 divided by the 16.0246 times 100, I get 25.13% hydrogen. If you added those two percentages together, you should get 100. Now, practicality, sometimes we get 99.97. That's okay. Or if we got 100.002. We're dealing in the real world here, and we're dealing with significant figures, so sometimes it just doesn't add up. Okay? Now, let me do one more example here with the formula for something that's a little bit more complicated. So let's say that I had, sodium sulfite, Na2SO4. Well, we know that in sodium sulfite we have 2 moles of sodium. So that's going to be 2 times 22 let's see what your book uses. 22.99. No, that's what I want, sodium sulfite.
You said SO4.
No, I said sodium sulfite, SO3.
Okay, I thought I heard you say SO4.
Okay, sodium sulfite, 2 times 22.99 grams. We've got 1 sulfur, so we've got 1 mole of sulfur. So that's 1 times 32.06 grams. And we've got 3 moles of oxygen, so 3 times 15.9994 grams. Okay? So 2 times 22.99 gives me 45.98 grams of sodium. And then I have 32.06 grams of sulfur. And then 3 times 15.9994 is 47.9982 grams of oxygen. So 45.98 plus 32.06 plus 47.9982. Now these two in 2 places past the decimal, so when I add this up, I get 126.84 grams, because I can only go 2 places past the decimal. Okay, so our percent sodium would be 45.98 divided by 126.84 times 100%. I went ahead and dropped the grams because they're going to divide out. So 45.98 divided by 126.84 times 100, I get 36.48%. Our percent sulfur would be the 32.06 grams or 32.06 divided by 126.84 times 100%. 06. So I get 25.44% sulfur. And then lastly, our percent oxygen is going to be 47.9982 divided by the 126.84 times 100%. And I get 37.84% oxygen. If you add all those up, I get 99.76. That's okay. With rounding and things, that's expected. If you got something like 82%, you would know something was terribly wrong. Okay? Now, let's think about going the other direction. In a lab situation, how am I going to use percent composition to help me determine the formula of a compound? Because if I can go to a formula to percentages, I ought to be able to go from percentages back to formula. Okay? So, we're going to start out with how to determine an empirical formula. Now, here are kind of the steps that we're going to use. Okay? We either start with percentage data, so mass percents, or mass parts. If you are a experimental chemist who does synthetic chemistry, synthesis is when you're making new compounds. You make a compound and you think you know what you made, but we're never 100% sure, especially when you're making something new. So what they do is they purify their compound, and the first thing they do is they send it off to a company that breaks their compound back into its elements. And they get a report back that says your compound is this percent carbon, this percent nitrogen, this percent sulfur, this percent oxygen. Give some percentages. And they take that percentage and they're going to find the formula. You also might get a report back that says your 7.6 gram sample contained this many grams of oxygen, this many grams of sulfur, this many grams of oxygen. Could come either way. If the information is in percentages, you just change the percentage sign to grams. Remove the percentage sign, replace it with grams. Once you've got everything in grams, you convert grams of each element into moles of that element using the molar mass. Okay? Remember, these numbers are not going to be whole numbers. Then you're going to start doing math tricks. Okay, we're going to divide each mole amount by the numerical value of the mole amount that is the smallest. No units on it, we're just dividing by that number. What we're trying to do is we're trying to create a whole number ratio. Okay? If the mole amounts after you've done step 3 are within 0.1 of a whole number, you can round to that. So if I had 1.07, it's within 0.1 of a whole number, I could round that to 1. But if it was 1.33, that's not within 0.1 of a whole number, I can't round. Scroll up for me. Okay, if the mole amount is not within 0.1 of a whole number, we're going to multiply all of the mole amounts by a number that will bring things to within 0.1 of a whole number. So if I had 3.21 moles of carbon, if I multiply by 5, I get 16.05, which is within 0.1 of a whole number, so I could round. And guys, this is a lot of trial and error. If it's not within 0.1 of a whole number, try multiplying by 2. 2 doesn't work, try multiplying by 3. 3 doesn't work, multiply by 4 until you find which one does. Okay? Usually 5 is about as high as you have to go. So we're going to try an example here. Okay? So we've got the following. We've got a compound, And we're told that it's 40.00% carbon and 6.71% hydrogen and 53.28% oxygen. Okay? So I want to take the percentages off and just change everything to grams. So 40.00 grams of carbon, 6.71 grams of hydrogen, and 53.28 grams of oxygen. Now my first step is to go from grams of each element to moles of that element. So 1 mole of carbon for every 12.011 grams of carbon. 1 mole of hydrogen for every 1.0079 grams of hydrogen. 1 mole of oxygen for every 15.9994 grams of oxygen. Okay, now this is embedded in my notes, but I'm trying to write it out for you so that you'll see it kind of like you do it working a problem. Okay, so for our carbon, we're going to get 3.330 moles of carbon. And for hydrogen, we've got 6.66 moles of hydrogen. And for oxygen, we've got 3.330 moles of oxygen. Now looking at this, the smallest numerical value here is 3.33. So I'm going to divide everything by 3.33. When we do that, I get 1.00 moles of carbon. I get 2.00 moles of hydrogen. And I get 1.00 moles of oxygen. Okay? Now, all of those are nice. They're within 0.1 of a whole number. So our empirical formula is CH2O. Okay? So now we're going to look at problem 4.14 on page 187. Yeah. So I've got it up here. Now, it says in 4.14, it says a sample of compound is decomposed in the laboratory and it produces 165 grams of carbon, 27.8 grams of hydrogen, and 220.2 grams of oxygen. Carbon, hydrogen, and oxygen combine to make a vast majority of compounds, a lot of them. So this time we're not given percentages, this time we're given grams. So we don't have to do that for first step. So this is 4.14. So let's look at this guy and start working it through. Okay, so we've got 165 grams of carbon. We've got 27.8 grams of hydrogen. And we've got 220.2 grams of oxygen. Okay, our first step here will be to go grams to moles. So 1 mole of carbon for every 12.011 grams of carbon. 1 mole of hydrogen for every 1.0079 grams of hydrogen. 1 mole of oxygen for every 15.9994 grams of oxygen. Now guys, don't panic. I don't expect you to have those memorized, but I have been doing this for a few years, so they've stuck. So notice that grams of each element divide out in this process. Let's pop through the numbers. So 165 divided by 12.011 gives me 13.7 moles of carbon. 78.8 divided by 1.0079 gives me 27.6 moles of hydrogen. And 220.2 divided by 15.9994 gives me 13.76 moles of oxygen. Now the smallest one in this group is 13.7. So I'm going to divide everything by 13.7. So 13.7 divided by 13.7 gives me 1.00 moles of carbon. 27.6 divided by 13.7 gives me 2.01 moles of hydrogen. And 13.76 divided by 13.7 gives me 1.004 moles of oxygen. Now, this is within 0.1 of a whole number. This is within 0.1 of a whole number. So my empirical formula would be CH2O. Notice we just got this same formula we did before, but this time we were starting from grams. Same compound or a related compound. Now, let's look at flip it back, because we're going to do 15. Let's look at problem 15. Okay? Here it says ibuprofen has the following mass percentage. It's 75.69% hydrogen, 8.80% hydrogen, and 15.51% oxygen. So we're dealing with the same three elements again. Okay, but we're probably going to get a different compound. So this is 14.15. So let's start working through this problem. Okay, so we've got 75.69 grams of carbon. We've got 8.80 grams of hydrogen. And we've got 15.51 grams of oxygen. So 1 mole of carbon for every 12.011 grams of carbon. 1 mole of hydrogen for every 1.0079 grams of hydrogen. 1 mole of oxygen for every 15.9994 grams of oxygen. So let's start doing our math. 75.69 divided by 12.011 gives me 6.302 moles of carbon. 8.80 divided by 1.0079 gives me 8.73 moles of hydrogen, and 15.51 divided by 15.9994 gives me 0.969 moles of oxygen. Okay? Now, the smallest numerical value in that set is a 0.969, and that should be 9694, because I should keep my 4 significant figures. So I'm divided by 0.9694. So on the bottom here, I get 1.000 moles of oxygen. 8.73 divided by 0.9694 gives me 9.01 moles of hydrogen, and 6.302 divided by 0.9694 gives me 6.5 moles of carbon. Now, guys, pay attention right here. That's not within 0.1 of a whole number. I can't round to a whole number here. In fact, that one's smack dab in the middle. Now, I happen to know when it's 0.5, I'm going to multiply by 2. So I'm going to multiply each one of those by 2. So if I do that, 6.5 times 2, that gives me 13 moles of carbon, and 9 times 2 gives me 18 moles of hydrogen, and 1 times 2 gives me 2 moles of oxygen. So I have C13, H18, okay, O2. And that's our empirical formula. Now, I really wanted you to see that one because we had to do that extra multiplication step. Okay? Now, once we have an empirical formula, if we are dealing with a covalent compound, we're also going to want to know the molecular formula. Okay? Now, to do this, we're going to need the empirical formula and the molar mass. When we look at the ideal gas law chapter and the beginning of next semester, when we look at colligative properties, I'll show you some ways that we can experimentally determine the molar mass. But you're going to have to take my word for it right now. It's a process we can do. So what we're going to do to go from an empirical formula to molecular formula is we're first going to determine the empirical formula mass by adding up the masses of all of the atoms listed in the empirical formula. Then we're going to take the molar mass and divide by the empirical formula mass. The units are going to divide out, and we're just going to get a number like 3 or 2 or 1 or 12 or 7. Okay? What this number does is it tells us the number of times the empirical formula repeats in the molecular formula. It tells us what we're going to have to multiply all the subscripts in the empirical formula by to get the molecular formula. So we're going to multiply each subscript in the empirical formula by the number that we got in step 2, and we're going to have the molecular formula. So we're going to look at problem 14.16. Okay? Okay, I think we're going to do both of these. That way you will have seen it all. So if we look at 14.16, it says a compound has an empirical formula of CH and a molecular formula, a molar mass, of 78.11 grams per mole. Okay, what is the molecular formula? So let me erase here. You guys look at that problem, kind of start sketching it out for yourself. So we're told that our empirical formula is CH, and our molar mass is 60.10 grams per mole. Okay? Now, this is one way to write the molar mass. You've been seeing me write it like this. 1 mole of whatever this is has a mass of 60.10 grams. Okay? This is just another way to write it. It's writing it in fractional form instead of in kind of long, these things equal form. So our step 1 is to calculate empirical formula mass. So 1 times 12.011 grams plus 1 times 1.0079 grams, because I've got 1 mole of carbon and 1 mole of hydrogen. So 12.011 plus 1.0079, that gives me 13.019 grams here. So to get our ratio, or your book calls it the factor. Doesn't that sound impressive? The factor. We're going to take the 60.10 grams and divide it by 13.019 grams, and the grams and grams divide out. Hold on. Did I write down the wrong? Yeah, I did. I'm sorry, guys. I've got two problems sitting there and I glanced wrong. 78.11 here. I happen to know what the answer to this one is, and I wasn't getting the answer I was anticipating. So 78.11 divided by 13.019, I get 5.999692727 on my calculator. Now, if I round this to 4 significant figures, I get 6.000. Okay? That's the factor. So our molecular formula is C6H6. It's a compound commonly called benzene. Okay? So let's look at the next one. And then I'll be done with these kind of problems. The next problem says that we have a compound whose molar mass is 60.10. I'm sorry, I mixed parts of the problems up. And it's got a percent composition of carbon of 39.97, hydrogen 13.41, and nitrogen 46.62 grams. So I'm going to have to calculate the empirical formula before I can get the molecular formula. Okay? So we know we've got a molar mass of the 60.10 grams, and we're given that we've got 39.97 grams of carbon for every 100 grams and 13.41 grams of hydrogen and 46.62 grams of nitrogen. A new element, yay! So 12.0, let's see, 1 mole of carbon for every 12.011 grams of carbon, 1 mole of hydrogen for every 1.0079 grams of hydrogen, and 1 mole of nitrogen for every 14 I don't have nitrogen memorized all the way out, 14.01 grams of nitrogen. So 39.97 divided by 12.011, it's 3.328 moles of carbon. And 13.41, I know my 4 is funky there, divided by 1.0079 gives us 13.30 moles of hydrogen, and 46.42 divided by 14.01 is 3.328 moles of nitrogen. Now notice 3.328 is my smallest. So 3.328 divided by 3.328 divided by 3.328. So that gives me 1 mole of nitrogen and 1 mole of carbon, and 4 significant figures, I get 4.000, well actually, I get 3.997 moles of hydrogen, but that's going to round to 4. So our empirical formula is CH4N. So we got part 1 of the problem done. We've got our empirical formula. Now let's get our empirical formula mass. So I'm going to go 1 times 12.011 grams plus 4 times 1.0079 grams plus 1 times 14.01 grams. Add all that up. And that gives us 30.05 C. That's as far out as I can go, 2 significant figures. Okay, so to get the factor, I'm going to take 60.10 and divide it by 30.05, and I'm going to get a big whopping 2. So our molecular formula is going to be C2H8N2. Okay? Now, these are all very similar problems. You just got to follow the process. And if you do the process, you're going to be good. Now, you guys can skip combustion analysis. It's on page 189. If you are so if you're pushed to do analytical chemistry, you'll do combustion analysis, but we're not going to do it. And I'm skipping section 4.12, okay? Because you'll take organic chemistry later, okay? So let's see what our next topic is. That's the end of that. So this is where I'm going to end this lecture, and we'll start with our next topic next lecture.